Exactly. Yes.
Okay. So let's continue our study of mechanism design. So just to briefly recap, we learned about the VCG mechanism, which in some sense solves a huge fraction of the problem space in mechanism design, right? You could define these sort of arbitrary spaces of alternatives you could choose between. This captured not just single item auctions, but complicated multi-unit auctions with constraints, public projects problems, and the VCG mechanism, no matter what, would solve those problems in a way that maximized welfare, was dominant strategy incentive compatible, was budget balanced, and was individually rational. And we ended that lecture, it was sort of a remarkable result, but we ended the lecture by sort of complaining about the things that it didn't do. Now, one of those things was handle objectives other than welfare. And we spent last lecture characterizing exactly when you can and cannot implement truthfully some objective. And it turned out to be exactly when the corresponding allocation rule was monotone. But there was another problem with the VCG mechanism that we sort of hinted at, which is that even when your objective is welfare, even when the thing that you care about is choosing the alternative that maximizes, this utilitarian some happiness objective, that sort of step one in the VCG mechanism, this step that when we were talking about it, we didn't dwell on very much, was just, like choose the alternative that maximizes social welfare, right? Like we sort of, in the VCG lecture, the way we were speaking about this was that the allocation rule wasn't very interesting. If we wanted to maximize social welfare, our hands were tied. We had to just choose the welfare maximizing allocation. And the only thing to focus on was the payment rule. And that's true as far as it goes, but this problem of maximizing welfare, which is easy enough to write down, choose the alternative that maximizes some bidder valuations. If the space of alternatives is very big and complicated, this might be easier said than done, right? Like this is not necessarily a computationally tractable task. And so the question I want to ask in this lecture is, what if we're in a setting that is in principle solved by the VCG mechanism? We want a truthful mechanism, that's budget balanced, individually rational, all of those nice things. And indeed, the thing that we care about is maximizing social welfare, but we just can't solve this problem exactly because it's complicated. Suppose it's NP hard. Okay, like what do we do in that case? And if you've taken an algorithms class, a natural idea you might have at this point is, you might say, look, sure, there's plenty of complicated problems that we can't solve exactly. And some of the real world auction problems we've hinted at, like auctioning off takeoff and landing slots at American airports or auctioning off radio spectrum across the United States, are examples of such problems. Like they're NP hard, not just in principle, not just in the worst case, but like we really don't know how to solve these problems, the real instances of these problems exactly. But like often we can get pretty good approximations, right? Like either maybe you have like an algorithm that's an approximation algorithm that has some provable approximation guarantee, say it always gets you within 99% of the optimal welfare. Or maybe you don't have that, but you've got pretty good heuristics. You write down an integer program and you run Cplex on it, and it gives you a pretty good solution. So if the only thing you were interested in was solving the algorithmic problem, then that would be great. You'd be done, right? You sort of try to solve your integer program. You sort of give a best effort solution, and to the extent that it approximates the optimal objective within 99%, like you're super happy. But the problem is, like, we're solving a more complicated problem than the algorithmic problem. We're solving the mechanism design problem. And our allocation rule interacts with our payment rule in very delicate ways. So if you sort of remember how our analysis of the VCG mechanism went, for every single statement we proved, like that it was dominant strategy truthful, that it was individually rational, that it was budget balanced. At some point, we relied on the fact that the thing we were computing, the allocation we were computing, was exactly the thing that maximized social welfare. And if you just sort of naively plug into that a solution that is 99% optimal, but not 100% optimal, then all of those guarantees can break catastrophically. It's not that if you approximate the welfare objective that you're approximately dominant strategy truthful or approximately budget balanced. Things can break catastrophically. All of your payments can become negative, for example. Okay, so like the problem is our analysis of the VCG mechanism, like in particular its incentive properties, really delicately depended on exactly solving the optimization problem. And so we need something more clever than just sort of plugging in our, state-of-the-art approximation algorithms when we encounter a, like a computationally hard allocation problem. Okay, so this is sort of the problem that sort of I want to point out, and for the rest of the class, what I'm going to sort of walk through is a particular case study, something I'll call Knapsack auctions, that is an example of working through a solution to one time this can arise, but more generally, you should think of this as an exemplar. Like there's all sorts of hard allocation problems beyond what we're going to see today, and you'd need to go through a similar exercise for all of them. So let me stop here and just ask whether the problem that we want to solve makes sense. Like the VCG mechanism was great, but like we just assumed in the analysis that we could solve this optimization problem. We didn't think twice about it. The setting we were operating in was very general. So the set of alternatives could be extremely large, right? If I'm giving out bundles, even just for auctions of goods where I'm selling stuff to people, if I'm selling K items, but you might want more than one of them, then there's 2 to the K bundles that any particular person could get. It's, like very quickly it becomes impossible to just enumerate all solutions. And so you need a more clever algorithm for this, and sometimes they don't exist. Okay, so is the problem clear? Yeah. Yeah, so if you sort of revisit the proofs for why, for example, the payments are always positive, right? Like we're sort of subtracting, what are we? We end up sort of comparing the, your negative externality. We were just looking at your negative externality by entering the auction. So we're sort of looking at the difference between the exactly welfare maximizing solution on everyone else, assuming you did participate, and the exactly welfare maximizing solution on everyone else, given that you did not participate. And since it's a difference, so that's, first of all, that's 2 of these NP hard problems we might have to solve. What's the welfare maximizing solution with you, and what's the one without you? And suppose we solve the first one to within 99% of optimal, and we solve the second one to within 99.5% of optimal. All of a sudden, like the magnitude of the difference can change by quite a lot. Does that make sense? Yeah. Okay, so is the problem clear? Okay, so as our sort of case study in thinking about this problem, I want to think about something called a knapsack auction, which is related to the knapsack problem in combinatorial optimization that you might have encountered before. The idea is the following. We've got n bidders. Oh, and maybe just to have like a concrete example in your mind as I'm describing this, maybe think about the problem of auctioning off airline seats on like airplane seats on like a particular airplane. Okay, so there's like what's going to happen is I've got a particular number of seats on my airplane, and I've got different groups of people who want to travel on my airplane, but each group might have a different size. So there might be sort of solo business travelers, there might be families of 5, there might be like a volleyball team. It's got however many people a volleyball team has on it. And the point is none of them want to be broken up across different trips, right? Like if I have a family of 5, I don't want like, 4 tickets on like this airplane, and then I send my 2-year-old on like the following one. Okay, so maybe this is something you can keep in mind just as a exemplar as we talk about the abstract problem. So we've got n bidders. Think of each bidder as one of these parties who'd like to get airline tickets. And they each have a publicly known size, which I'll call Wi, and think of as the number of members of the party. Okay, there's the family of 5, they have size 5. There's the solo business traveler, they've got size 1. There's the volleyball team that's got size equal to however many people are on a volleyball team. Okay, so this is, we're going to assume that the size is not something that people are going to like misreport. Like I'm not going to try to like only buy 4 airline tickets, even though secretly I need 5. Like the size we're assuming is like publicly reported. And the mechanism has what I'll call a public budget B, which you should think of maybe in this example as the number of seats available on this airline. Like maybe there's 100 seats to sell. And what I can do is I can decide which of these parties, which subsets of these parties get to fly on my airplane, but like subject to the budget constraint. So the set of feasible alternatives in this mechanism design problem are all subsets of bidders whose cumulative size is at most B. Okay, so I can serve any subset of these parties such that the total number of airline seats they need is less than B, the number of seats on my airplane. Make sense? Okay, so this is subsets of n items. So we're talking about we're starting to talk about a combinatorially large set of alternatives. There might be lots of subsets of n items. And just notationally, like an alternative written this way is a subset of the bidders. But let me abuse notation a little bit and pretend that A is like a vector, just the indicator vector for the subset. And I'll just write AI equals 1 to mean that party I is served. Bidder I is one of the winners of the auction, and AI equals 0 otherwise. Okay, so AI will just be like an indicator 1 or 0, specifying whether they were one of the winners of the auction or not. And we're going to think about these as single parameter domains, where we sort of imagine that everyone prefers to win the auction than to lose the auction. And if they lose the auction, they don't care which subset of people won it. And so the only thing that we don't know is what their value is for being served. So every agent, every bidder will have this sort of secret, this private number VI. And if I choose alternative A, bidder I's value is VI times AI, which just means their value is VI. If they win, they get to go on the airplane and take the trip, and it's 0 otherwise if they lose. Okay, and the reason I'm writing it this way is because I want you to see that this problem is a single parameter domain, as we talked about last class, so that we can use our characterization for last class about what our design space is for just coming up with a truthful mechanism. Okay, so is the problem definition clear? Is it clear what a knapsack auction is? Okay, So the reason these are called knapsack auctions is because the welfare maximization problem, which the VCG mechanism would need to solve, which is just find the sort of set of feasible allocations that maximizes the total value amongst the agents subject to my budget constraints, right? This is just the welfare maximization problem, is like a famous combinatorial optimization problem you've probably seen before in like an algorithms class called the knapsack problem, and it's NP hard. Okay, so like in particular, like since the allocation, this is the allocation rule for the VCG mechanism, there is no polynomial time algorithm probably for implementing the VCG mechanism for knapsack auctions. And if we want to have a polynomial time mechanism for solving knapsack auctions that has nice incentive properties, we're going to have to come up with something else. Okay, so this is a concrete exemplar of the kind of issue we were just talking about, where the VCG mechanism would be great if only you could run it, but we don't have polynomial time algorithms for running it in this case because the welfare maximization problem is a combinatorially hard problem. Make sense? Okay. So, like, what should we do? So like, if our goal is to come up with a polynomial time algorithm that has the incentive properties we want, well, of course, we can't hope to exactly maximize social welfare anymore, since we know there aren't, forget the incentive properties, there aren't polynomial time algorithms that exactly optimize social welfare in this problem. But like, okay, our goal is to have an approximation algorithm that always approximates the social welfare objective. But we'd like to pair it with a pricing rule that makes truth-telling dominant strategy truthful, and hopefully also is individually rational and budget balanced and has the other nice properties of the VCG mechanism. And we know that like we can't just pick our favorite approximation algorithm for knapsack and pair it with the VCG pricing rule. In fact, we can't, we can't even compute the VCG pricing rule. Like to figure out the prices for the VCG mechanism, you also need to solve the welfare maximization problem. So we need to come up with an approximation algorithm for knapsack, and we need to pair it with a pricing rule that makes truth-telling dominant strategy truthful, that makes truth-telling a dominant strategy. And so, like naively, if we hadn't had last lecture, this might be a tricky problem, right? Because coming up with an approximation algorithm is sort of already kind of a hard problem on its own. And like somehow we would need to like simultaneously come up with an approximation algorithm with it together with a matching pricing rule that makes truth-telling a dominant strategy. But because this is a single parameter domain, and because we had last lecture, we actually don't need to solve the pricing problem, right? Like, what did we learn last lecture? We learned that an allocation rule can be made dominant strategy truthful, meaning can be paired with a pricing rule that makes truth-telling a dominant strategy, if and only if the allocation rule is monotone non-decreasing. Right? Like last lecture was sort of a reduction from a mechanism design problem to an algorithm design problem. That is, if our allocation rule is not monotone non-decreasing, then we know that we don't have to try to think hard about pricing rules. They just don't exist. There are no pricing rules that make non-monotone allocations truthful. And if we do have a monotone allocation rule, we also don't have to think hard about pricing rules because the pricing rule was given last lecture generically. So to solve the knapsack auction problem, we just need to solve a well-defined algorithm design problem. We need to come up with an approximation algorithm for the knapsack problem that is monotone non-decreasing. Okay, it's just like another constraint on our algorithm design problem. Okay, some algorithms, some approximation algorithms are monotone non-decreasing, others are not. We need to, if we want our algorithm to be able to be turned into a mechanism that is dominant strategy truthful, we need to figure out an approximation algorithm that does have this monotone non-decreasing property. Okay, does that make sense? So we're getting sort of a lot of mileage out of this characterization from last class. It's making the problem we need to solve here a lot simpler. Is that clear? Okay, so let's review maybe some basic definitions. Let me remind you what an approximation algorithm is. Let me remind you what the monotone non-decreasing constraint looks like in this setting, and then we'll think about how we might be able to achieve both of them together. So first, maybe some notation. Like what's an instance of the knapsack problem, or what's an instance of a knapsack auction? Well, for each of these n bidders, I need to tell you two numbers. I need to tell you what their value is, and I need to tell you what their weight is. Right? How much do they collectively value flying on the airplane, and how many people are there in their party? Okay, so I can think of them both as vectors, right? Like V specifies a value for each of the n bidders, and W specifies a weight for each of the n bidders. Okay, so if I give you these two vectors, V and W, I have communicated to you an instance of the knapsack problem or an instance of a knapsack auction. And so let me write opt of VW as my notation for the value of the optimal solution for the instance of the knapsack problem given by V and W. It is just the social, it is just the social welfare maximizing, it is the social welfare of the social welfare maximizing solution of that instance. Okay, so it's just the maximum among all feasible subsets of bidders, all subsets of bidders whose weight is below the budget of the social welfare obtained by that solution. Okay, so like on every instance, the VCG mechanism would obtain social welfare opt of V and W. We would like to do that as well, except it's computationally hard. So since we are going to want to design a polynomial time algorithm, we're going to have to settle for something that doesn't always obtain this benchmark value opt, but we'd like it to not be too far off. So we'll say that an algorithm, which takes as input an instance of the knapsack problem and outputs a solution, a subset of bidders, is an alpha approximation algorithm for the knapsack problem. If, no matter what instance we plug into the algorithm, for every instance defined by V and W, two things should be true. Like first, it should always output a feasible solution. It should never sell more tickets than there are on the airplane. And second, the social welfare of the solution it produces should always be comparable to opt. Should always be at least the value of the optimal social welfare solution divided by alpha. So for example, if I say I have a 2 approximation algorithm, that means that the algorithm always is guaranteed on every instance to output a solution whose social welfare is at least half of that of the optimal social welfare. Does that make sense? So, the VCG mechanism would be a 1 approximation algorithm, but it wouldn't run in polynomial time. Our goal is to come up with an algorithm that does run in polynomial time and is an alpha approximation algorithm for hopefully some value of alpha that's not too big. Make sense? Okay, so we want to come up with an alpha approximation algorithm. And so that we can pair it with a payment rule that makes truthful reporting a dominant strategy, we'd like to make sure that our algorithm is monotone non-decreasing. So let's just remember what that means in the context of our problem here. What monotone non-decreasing means is that no matter what the instance is of the knapsack problem, fixing any V and W, And no matter what bidder I we care to look at, if bidder I raises their bid from VI to some higher value VI prime, well, generically, the monotonicity property means that bidder I should get an allocation that they prefer. And since here, there's only two things they care about, either they win the auction and get their airplane seats or they don't. All monotonicity means here is that if at bid V, I am a winner in the auction, I get seated on the airline, then I should also get seated on the airline at a higher bid V prime. Right? It should never be the case that I can raise my bid and go from winning the auction to losing the auction. The reverse can happen, right? It could be that I can go from losing the auction to winning the auction by raising my bid, but it should never be the case that at a lower bid I would have won and at a higher bid I do not. That is the monotonicity property we want to enforce on our algorithm. And if we can come up with an approximation algorithm that satisfies this monotonicity property, then we know from last class how to pair it with a payment rule that makes truth-telling a dominant strategy. Okay, is that clear? Okay, so for the rest of the lecture, we're gonna like ignore prices and incentives and just rely on last lecture for that, right? Like last lecture, we proved that this property on the allocation rule is sufficient to handle all of the incentive issues. And we're gonna take advantage of that. And for the rest of this lecture, we're just thinking about approximation algorithms that satisfy the monotonicity property. Okay, so let's start thinking about how to think about approximation algorithms. So I want to start by doing something that sort of is just syntactic. I'm gonna not do anything clever. I'm just gonna re-express the knapsack problem as an integer linear optimization problem. Okay, so say that I'm optimizing over these variables xi, one for each of the bidders. Okay, so there's n variables xi that are Boolean. They are either 0 or 1. And the meaning of xi is that if xi is 1, that means that party I is going to be seated on the airplane. Party I is a winner of the auction. And if xi is 0, then they're not, they lose. Okay. So in this case, I can just re-express the knapsack problem in the following way, where there's like this linear function that I would like to maximize, subject to a linear constraint. Okay. My goal here is to find values of the xi's, winners and losers of the auction, so that I maximize the sum over all of the bidders of xi times vi. Well, what is that? Well, it's just the sum of, right, like if xi is 0, then this term just zeroes out. So this is really just the sum over all of the I such that xi is 1 of vi, which is just the sum of the values for the people who win the auction, which is just the social welfare. Okay, so I'm trying to find an allocation that maximizes social welfare, subject to the constraint that the sum over all of the bidders of xi times wi is less than the budget. Again, if xi is 0, then the corresponding term just zeroes out. So this sum is just the sum over all of the bidders I such that xi is 1, all of the winners of the auction, of their weight. So this is just saying, I want to maximize social welfare, but subject to this constraint that the set of people I allocate, the set of people I decide are winners, must have total size that does not exceed my budget. Yeah. Oh, so VI is just, you know, however much your party values getting on the airplane, right? So like, it might be that the volleyball team that has however many people are in a volleyball team in it has a very high value reflective of the fact that there are probably lots of people on a volleyball team. Okay, so it's not like VI is, 0 or 1. Like it might be that the bigger parties have correspondingly bigger values, but maybe not, right? Like maybe even though the family of 6 going to Boca Raton, Florida, there's 6 people in them, like maybe their value for that trip is actually less than the value of like the business traveler who's going to close his like Series A round in Menlo Park or something. So anyways, yeah, like we're not assuming any relationship between the value of the party and the size of the party, but there certainly could be. Does that make sense? Other questions? Yeah. That's an input to the problem, right? So every bidder has a value, how happy they are if their party is seated on the airplane, and a size, how many people are in their party. So an instance of the problem is given by VI and WI, and I'm just writing down, this is just a different way to write down like the knapsack problem. I want to maximize social welfare subject to a budget constraint. Okay, makes sense. Okay, so like so far I haven't done anything. I've just written down the problem in this form. This is called an integer linear program. And it's not like I can just solve this. Like the fact that I'm able to express the knapsack problem as an integer linear program is actually a proof that integer linear programming too is NP-hard, right? So like I've just expressed this in a only more general optimization framework that is like also NP-hard. But like, are we all on the same page that this is still the knapsack problem? Okay, so like solving the integer problem is NP-hard, not clear what to do about it. But let me sort of make a philosophical point. Like when a problem is NP-hard, of course, so most directly that means we shouldn't expect to have a polynomial time algorithm that can solve it. But it also kind of means that we shouldn't expect to be able to productively reason about the structure of the optimal solution. Somehow, this isn't a rigorous statement. This is sort of a moral argument. But somehow we should expect that like NP-hard problems don't have lots of tractable structure around their optimal solutions, because if they did, we could exploit that structure to come up with efficient algorithms. And there are no efficient algorithms, so probably they don't have that structure. Now, our problem here in trying to come up with an approximation algorithm to an NP-hard problem is that we need to prove a theorem that relates whatever our algorithm is going to do to the optimal solution to every problem instance. And so even if, even though we can't solve this problem, and our intention is not to exactly solve this problem, we need to prove a theorem that somehow grapples with the optimal solution to this problem. And so mathematically, we're going to need to exploit some structure about that optimal solution, it seems. And maybe we should be worried about that because probably optimal solutions to NP-hard problems don't have a lot of structure. Okay? So that's one reason for having a little bit of anxiety at this point. And so instead, what I want to think about is a relaxed version of the same problem. That looks very similar to what was on the last slide. Okay, we still have these, it's still an optimization problem over these variables, xi, one for each bidder. We're still maximizing the same objective, this social welfare objective. We're still subjecting ourselves to the same constraint, this budget constraint. The only thing that's different is that these variables used to have to be either 0 or 1. They were binary. You had to either assign someone as a winner to the auction or not. And now I've relaxed that constraint. I say these variables can actually be real numbers that take values between 0 and 1. Okay, so this is a syntactically very similar problem to what was on the last slide, but has this important difference, like the solution will no longer be integer, right? It's no longer clear what problem this optimization problem is solving, because this, like if your party gets, if your party I and you get xi is, 0.23, like what does that mean? And we'll have to think about that. But the reason I want to think about this problem is that this problem is called a linear program. This is an instance of a linear program. And this problem is solvable in polynomial time. We know how to solve linear programs efficiently. So somehow the thing that was making the knapsack problem hard, it wasn't these like linear constraints. It was this constraint that the xi's be integers, that they be either 0 or 1. And if we get rid of that, of course, it's no longer clear what we do with the solution. Like it's not a solution to the knapsack problem anymore. But this kind of problem we have efficient algorithms for. Now, this is going to get back to the moral point I was making. The thing that I want to do next is not just solve this linear program, because it's not clear what we would do with the solution to this linear program. It gives fractional allocations, and we're not allowed to do that in the real problem. But the reason it's going to be useful for us to think about this linear program is because, related to the fact that linear programs are solvable in polynomial time, the optimal solutions to linear programs have some nice structure. And that's going to help us think about them. Okay. So let's call this the fractional problem. This is like the fractional knapsack problem. And the reason I'm calling it fractional is because, a solution to this problem might now assign a party like a, fraction of a seat on an airplane. Yeah. Say that again. Good question. Good question. Yeah. So let's give a name first to the optimal solution to the fractional problem. Let's say that opt f, given an instance v and w, let's say that opt f is the optimal value of the fractional problem. Okay, so this is not the problem. This is not directly the quantity we care about. We want to solve the integer problem, but I want to make a claim, a simple claim first, which is that for every problem instance, for every instance of the knapsack problem given by v and w, the optimal value of the fractional solution is only bigger than the optimal value of the integer solution. And can you tell me why? Yeah, exactly. Like the fractional version of the problem is only less constrained. Like before, the original problem required that these xi's be either 0 or 1. Well, if the xi's are either 0 or 1, in particular, they're between 0 and 1. So something that was a feasible solution to the original knapsack problem is also a feasible solution to the fractional relaxation, but the fractional relaxation might have more solutions. So in particular, the optimal solution to the knapsack problem, the optimal solution to the integer version of the problem, is a candidate feasible solution to the fractional version. So certainly the fractional optimum can't be smaller than the integer optimum, but it could be bigger because there might be solutions that really take advantage of this fractionality that get even higher objective value. Okay, so so sort of as a simple relationship between these two, we know that if we have an instance of the knapsack problem and then we take its fractional relaxation, all we've done is we've made the optimal value larger, not smaller. Make sense? Okay. So like, how is that useful to us, right? Like we need to come up with a solution to the original problem. Like our goal is to be able to find a solution such that we can prove that it always has welfare at least to opt over alpha. Now that might be hard to prove because we don't really understand the the structure of optimal solutions to the integer problem. But if we can prove the stronger theorem, that we always get at least an alpha approximation to the fractional version of opt, if we can come up with an integer solution whose welfare is always at least the fractional optimum over alpha, well, since the fractional optimum over alpha is at least the integer optimum over alpha, we will have accomplished what we wanted to. We will have come up with an alpha approximation to opt. Does that make sense? So we're gonna actually try to prove a stronger theorem than we need. Not only are we gonna try to aim for an alpha approximation to opt, we're gonna try to aim for an alpha approximation to the fractional version of opt. That's a stronger theorem than we need, but it might be easier to prove because we can take advantage of the additional structure that the fractional version of opt has. And since it's a stronger theorem than we need, it implies the theorem we want. That's going to be the strategy. Does that make sense? Okay. So like this whole plan is like premised on the assertion that the fractional problem has nice structure in its solution space. Okay, so let's like see if that's actually true. So here's going to be like the structure of the fractional problem we take advantage of, the simple structure of the fractional problem. Okay, so fix any instance of the knapsack problem V and W, and let X be an optimal solution to the fractional relaxation of the knapsack problem. Okay, so X maximizes welfare subject to the budget constraint, but it might like now fractionally assign people seats. So then the claim is that X must have the following structure. Pick any two people I and J, such that when I compare like what I'll call the value density for I, by which I mean their value divided by their size. Okay, so the business traveler who really wants to get to Menlo Park to close his Series A has very high value density because his value is very high and his size is very small. The family of 12 that wants to go to Boca Raton, Florida, but they're not going to really enjoy it because there's so many kids. They have very low value density because their value is small and their size is large. And the claim is if I have two bidders I and J, such that bidder I has higher value density than bidder J, then if in the solution bidder J is assigned any seats at all, even fractionally, then it must have been the case that we fully satisfied the demand of bidder I. That is, we won't satisfy the demand of any bidder J until we have fully satisfied the demand of every single bidder I who has higher value density. That's the claim. Okay, this is a claim that like optimal solutions to the fractional problem have to have this structure. The claim makes sense. Okay, so let's prove it. Suppose this were not the case. What would that mean? That would mean that there was some instance of the knapsack problem given by V and W that had an optimal solution X such that there was a pair I and J such that indeed I had higher value density than J. But in the optimal solution, bidder J had their demand partially satisfied, right? Satisfied to a degree strictly greater than 0. And bidder I's demand might also have been partially satisfied, but was not fully satisfied. This is the thing the lemma says shouldn't happen. That I has higher value density than J, but Xi is not fully, bidder I is not fully satisfied and bidder J is already partially satisfied. Suppose that were the case. Then let me define, like, what's the strategy of the proof here, just to like look a step forward. We want to say if this is the case, then I can find you a different solution that is also feasible and has higher welfare. And that's a contradiction because X is supposed to be the optimal solution. Okay, so our goal, if we're given such a solution, is to perform a little surgery on it, to like actively modify it, while maintaining the feasibility conditions and strictly improving the welfare. Okay, that'll be a contradiction because the premise here is that X is the optimal solution, so I shouldn't be able to do that. Okay, so I want to define this number delta, which is going to be the smaller of the following two quantities. It's going to be the smaller of xj and 1 minus xi weighted by the ratio of bitter i's size to bitter j's size. And for now, the only thing I want to notice about this quantity is that it is positive. It's strictly positive. Why? Well, by assumption, xj is bigger than 0. And xi is less than 1, so 1 minus xi is bigger than 0. So we're taking the minimum of two terms that are positive, so this is some positive number. Okay, so I want to define a new solution x prime and argue that it is feasible and that it has higher objective value than x, and that's going to be my contradiction. That'll contradict the optimality of x. Okay, so here's how I construct the new solution x prime. So first of all, like what I'm going to do is I'm going to mess with the allocation to bitter I and to bitter j. I'm not going to mess with anyone else's. So for any bitter L that is not I or j, their allocation in x prime is exactly the same as their allocation in x. The only messing I'm doing is between bitter I and bitter j. Now what I'm going to do is I'm going to give bitter j slightly less stuff. I'm going to lower the allocation to bitter j. I'll subtract delta off from it. And I'm going to give bitter I slightly more stuff. I'm going to increase the allocation I'm giving to bitter I. I'm going to increase it by delta times the ratio of wj to wi. Okay, less stuff to bitter j, more stuff to bitter I. And we need to show two things about x prime. One, that we haven't violated the feasibility constraints, that x prime still satisfies the budget constraint, and that x prime has strictly higher welfare. That'll be our contradiction. Okay, so first, let's check that we haven't violated the knapsack constraint. So how much did we change the total size of our allocation? Well, on the one hand, we made it bigger, right? Because we increased the allocation to x prime. Well, how much bigger did we make it? Well, we increased the allocation to x prime by exactly delta times wj over wi. And bitter I has size wi, so we have to multiply that by wi. And the wi's cancel out, the numerator and the denominator. But we made some additional room because we subtracted off delta from bitter j's allocation. How much additional room did we make? Well, bitter j has size wj, so we made delta wj additional room. And so the additional space we're taking up with bitter I exactly matches the additional room we made by subtracting off allocation from bitter j. And so we haven't changed the size of the bundle. And so if we satisfied the knapsack constraint before, we still satisfy the knapsack constraint. It's also important that we haven't made either xi prime or xj prime either bigger than 1 or less than 0, right? The xi's were supposed to be between 0 and 1. But that's true because of how we define delta. Remember, delta is only smaller than xj by definition. So subtracting delta off from xj leaves xj prime non-negative. And similarly, delta is only smaller than 1 minus xi times wi over wj. And so adding delta times wj over wi, the amount we're adding to bidder I, makes sure that xi prime doesn't exceed 1. So we still satisfy all of the feasibility constraints. And this xi prime solution, it's still a feasible solution, right? We haven't talked about its objective value yet, but like it's still feasible. Okay, so because x was feasible, x prime is also feasible. Now, how much did we change the value of the solution? We need to claim now that x prime has strictly higher objective value. Well, we changed it in 2 ways. By increasing the allocation to bidder I, we increased the value of the allocation by exactly the value of bidder I, vi, times the amount of the increase, delta times wj over wi, and we decreased the value by decreasing the allocation to bidder j. Well, we decreased the allocation to bidder j by delta, so we decreased the total welfare there by delta times vj. And we need to argue that this change in welfare is strictly positive. But it is, and it's because by assumption, right, the whole premise of this was that bidder I had strictly higher value density than bidder j, right? vi over wi, we assumed, was strictly bigger than vj over wj. And so just multiplying both sides by wj, right, like this was our assumption, multiplying both sides by wj, that just means wj over wi times vi, this quantity that we're adding, is bigger than vj, this quantity we're subtracting. And so x prime is a better solution than x, which is a contradiction because the assumption was that x was the optimal solution. And so we've proven that optimal solutions to fractional knapsack problems have to have this simple structure where we just sort people in order of their value density and allocate them fully in this order until we run out of space. Okay, makes sense. Okay. So now, if we want to think about the fractional version of the problem, we don't need to write it out as a linear program anymore. Having realized that it has this special structure, we can just write down the following simple combinatorial algorithm for the fractional knapsack problem that is like super easy. We just sort the bidders in decreasing order by their value density and keep track of how much space in our knapsack, on our airplane we've used so far. And in this sorted order, just march down the list and say, look, can I make, if I make the next bidder on the list, bidder I, a winner, will that still satisfy my knapsack constraint? Will the current size I've taken up so far plus the full weight of bidder I, will that still be less than my budget? And while that's true, I'll say, okay, well, hey, bidder I, congratulations, I'm fully satisfying your demand. And I'll do the bookkeeping to keep track of how much space I have left. And at the end, we get to this final bidder I, whose demand I cannot fully satisfy, right? Like it's the volleyball team. They've got however many people are on a volleyball team, but like I have 2 seats less than that on the airplane. Well, it's the fractional knapsack problem, so no problem. I just fractionally allocate them. I allocate the fraction of them that will fit on the airplane, and I call it a day. Okay, this algorithm has to give us the optimal solution to the fractional knapsack problem because of the structural result we just proved. To do anything else would violate the structure that we just proved optimal solutions must have. Okay, makes sense? Okay. Now, of course, like, what do we do with this? Like, this is not a solution to the knapsack problem because it's sort of like almost a solution to the knapsack problem, right? Like, you might have worried a priori that by allowing fractional allocations, we would get completely nonsense solutions where every bidder is allocated fractionally. But at the very least, that doesn't happen. Like there's at most one bidder in the optimal solution who's allocated fractionally, right? Like what this algorithm does is it fully allocates bidders in this descending order of sort of value density until it can't anymore. And then for the last person on the list, it gives them a fractional allocation. Yeah. We don't have to. We can break ties however we want, in which case the previous lemma would just say that there exists a solution that has this structure. Okay, so you might, so our question is like, does the existence of this algorithm tell us anything about how to get a solution to the integer program, the integer problem? And like, you might be encouraged by the fact that until this last step, this algorithm really is constructing an integer solution. It's just like at the last step when it's not. And so like your first thought might be like, okay, why don't we just like skip the last step? Like, why don't we fill up the airplane in order of, value density? And then when we get to the first party that doesn't fit, it's like, okay, we can't fractionally allocate them. What if we just say, sorry, like I'm going to fly with however many empty seats there are? Like that's not going to be the optimal solution, but it's only going to leave off one person. Well, why don't we just do that? So what do people think? Is that a good idea? Yeah, so like that's not a good idea because you might end up with a ton of empty seats. And maybe here's like an example. Okay, so let's suppose there's two bidders and one of them is big and valuable. Okay, one of them has size 10 and value 10. And the other one is, small and not valuable. It has size 1 and value 1.1. And suppose our budget is 10. Okay, so big valuable agent, small not valuable agent, but it happens that the small not valuable agent has slightly higher value density, right? The big valuable agent actually has value density 1, whereas the small not valuable agent has value density a little bit higher, 1.1. So we have 10 seats on our airplane. Like the optimal solution is obviously to seat, but like we can only seat at most one of these parties. They're not going to both fit. The optimal solution is obviously to seat the big valuable party, and then we get, welfare 10. But what is the algorithm we just proposed going to do? Well, it's going to sort people by value density. So the small, not valuable customer is going to be first in the sorted order. It's going to seat them. They only take up one seat. We're going to have 9 empty seats, and we're going to say, look, we don't have room for the valuable customer anymore. Like, too bad. And so that algorithm will get value only 1.1 when it could have gotten value 10. Okay, so it's like, could be as bad as a 10 approximation. And there's nothing special about 10. You could have come up with a version of this example where the algorithm we considered doesn't even get a 1/100 fraction of the optimal welfare, or a 1/1000 fraction, or a 1/1,000,000 fraction. So like this algorithm that just runs the optimal algorithm for the fractional knapsack problem, but then skips the last step because it can't allocate things fractionally, it is not an approximation algorithm for any finite value of alpha. So that's no good. Okay, so right, the problem was like, optimizing in this bang for buck order might leave the whole plane empty. So here's maybe a second attempt. Suppose we sort the bidders in decreasing order again by their value density. And we do the same thing we did before. While there's still room on the airplane for the next party in this sorted order, we make them winners of the auction, temporarily at least. We consider that they are candidates to be seated. Okay. And at the end, we have this candidate allocation S, which is exactly what the algorithm that we just thought of that wasn't very good would have allocated. It's just the prefix of people in the bang for buck ordering that fit on the airplane. And we'll consider outputting that, but we won't output it just yet. We'll say, look, there's this last guy in the ordering that the fractional solution would have fractionally allocated. He won't fit in our solution. But we'll ask, does the cumulative value of the solution that we've just come up with exceed the value of just this one guy that the fractional solution would have fractionally allocated. If it does, then we go ahead and we output this set S that our previous algorithm would have done. But if it doesn't, if we end up in like something like the bad situation from the previous algorithm, where this set S consists only of like the low value bidder, and this guy I at the end, he's the high value bidder, then actually what are we going to do? We're going to scrap this solution S, and what we're going to do is we're going to output a solution that seats just a single bidder. Which bidder? Well, the single bidder that has the single highest value. And if you want, if there's empty seats on the airplane, you can seat them to however you want. But we're going to analyze the algorithm as if you only seat this one guy, and even in that case, something good will happen. Of course, you wouldn't really need to leave all of the other seats empty. Okay. So is the algorithm clear? So it's sort of like what we were doing before, just sort by bang for buck, leave off the last guy who we can't allocate fractionally, but it just has this like little band-aid at the end, this little sanity check that says, look, if the cumulative welfare of the entire solution you're proposing is not as high as like, allocating to like a single bidder, then allocate to the single bidder instead. Okay. So the claim is that this band-aid is enough. You sort of patch up the algorithm by putting this band-aid on it. Not only does it solve this like one bad example for our first idea that we went through, but like actually on every possible input, it is guaranteed to give to obtain welfare that is within a factor of 2 of the optimal welfare. In fact, like we're going to prove something even a little bit stronger than that. It'll obtain welfare that's within a factor of 2 of the fractional optimum, which is only larger. Okay. So let's think about this. So remember, our algorithm enumerates people in this sorted order of value density. And what is this set S? It is just the largest prefix of that sorted order that do not exceed whose size does not exceed the budget, whose total number of demanded seats does not exceed the number of seats on the plane. And then there's this guy I, who's the first person in this sorted order who didn't make it into the set S. Okay. Now, we know that the fractional solution, the fractional optimal solution, what does it look like? Well, it fully satisfies the demand of everyone in this set S, this prefix of people in the density sorted ordering. And then it fractionally satisfies the demand of bidder I, after which the knapsack is full and nobody else gets their demand satisfied. So we know that in the fractional optimal solution X star, any bidder J who is not either in this set S, this prefix in the sorted ordering that fully fits on the plane, or is this guy I, who's the first person who didn't get their demand fully satisfied, in the fractional optimal solution, every other bidder J gets nothing. Right? That was because of what this optimal algorithm for the fractional optimal solution looks like. So the fractional optimal solution, what welfare does it get? Well, it fully satisfies the demand of everyone in this set S. So it gets welfare equal to the sum of the values of the people in this set S. And then it fractionally satisfies the demand for this bidder I. So it gets some fraction of his value. And that's it. So if we consider the sum of the values for everyone in the set S and bidder I's value, that's only larger than the fractional optimum, right? Because the fractional optimum gets this and then only gets a part of bidder I's value. And similarly, the fractional optimum is only larger than the integer optimum, the optimal solution to the actual knapsack problem. And so if I've got these two quantities that I'll call like A and B, say, and I know that A plus B is at least opt, then it's got to be that either A is at least opt over 2, or B is opt over 2. If they were both less than opt over 2, then their sum would be smaller than opt. So I know that the maximum of the welfare obtained by seeding everyone in this set S, and the welfare obtained by seeding the first person who didn't make it into this set S, VI, the better of those two welfares has to be at least opt over 2. And what does our algorithm do? Well, it actually doesn't take the better of these two things. It takes the better of the welfare obtained by the set S and the welfare obtained by seeding the single guy who has the highest value, VI star. But by definition, VI star is only bigger than VI. VI star is the largest value. And so the welfare obtained by our mechanism, which is the largest of these two quantities, is at least opt over 2. Okay? So it's a 2 approximation algorithm. Does that make sense? Okay. So like we've designed an approximation algorithm, but remember, like our goal was to solve a mechanism design problem. We wanted to design a truthful auction for the knapsack, the knapsack auction problem. And remember, in order to, we know since this is a single parameter domain, like we've got a particular algorithm here. We have a very simple way of determining whether we can pair it with a payment rule that will turn it into a truthful auction. Right? That was what we spent last lecture characterizing. We will be able to take this algorithm we just developed and use it as an allocation rule and turn it into a mechanism by pairing it with a payment rule that is dominant strategy truthful, exactly if the algorithm we just designed is monotone non-decreasing for every agent I, which remember just means must have the property that if agent I at a given bid wins, gets their demand met, then they must also win. They must also get their demand met at every higher bid. Okay, so to establish, we've established the algorithmic properties of our allocation rule. So it's a 2 approximation algorithm to the knapsack problem. To establish the incentive properties, we need to establish that the allocation rule is monotone non-decreasing. And if we can do that, we can look up the slides from last lecture and come up with a concrete payment rule, right? Just reading it off of the slides from last lecture to pair with this allocation rule, and we'll have a truthful mechanism. Okay. So let's verify that the mechanism is monotone. Remember, what we need to do is we need to establish that if at some bid profile, bidder I wins the auction, gets allocated seats, then if they raise their bid, they must still win. And we just have to like think about this in a couple of cases, because there's 2 different ways you could win this auction. Right? Like, remember, what does the allocation rule do? It sorts everyone by their value density and comes up with this candidate solution, the prefix of people in sorted ordering, the largest prefix of people in sorted ordering who fit on the plane. Now it might output that solution, but it might also output the singleton set that contains the single bidder who has highest value, who might not have been in the original solution. So there's 2 ways to be a winner. Either you could be in this set S, come up with by the algorithm, or you could be the highest value bidder. Okay. So let's fix any instance of the knapsack problem given by weights and values. And let's zoom in on some agent I. Okay. And let's say that VI is his original bid. And let's say that VI prime is some higher bid that he might consider making. Okay. And let's just call the bid vector v prime, the vector that comes from leaving everyone else's bid fixed, but letting bidder I unilaterally deviate from vi to vi prime. And let's say that if we run our algorithm with bids v, the solution we get is t. T is the set of winners of the auction. And if we run our algorithm with bids v prime instead, in which bidder I has raised his bid, let's say the solution is something else, call it t prime. These are the winners of the auction. And so the thing we need to show is that if I is in t, if I wins at the lower bid, then I is also in t prime. I wins at the higher bid. Okay. So remember this mechanism, there's two ways to win the auction. There's two, internally the mechanism generates this set S, which is just the largest prefix in density sorted order that fits on the airplane. S may or may not be the same as T. Right? T will either be S or it will be the singleton set consisting of the highest value bidder. But whether or not S is the same as T or not, let's just give a name to S. When I run the algorithm on the original bid vector V, let's say that S is the name of this intermediate set, the largest prefix in value in density sorted order that fits on the plane. And similarly, let's call this set S prime when I run the algorithm on bid vector V prime. Okay. So S is this prefix of bidders that fit on the plane when the bids are V. S prime is the prefix of bidders that fit on the plane when the bids are V prime. So we need to argue that if I is in T, then I is in T prime, the actual winning set. T may or may not be S, T prime may or may not be S prime, but as an intermediate step, I want to just argue that if I is in S, if it's in this prefix of bidders who fit on the plane, then I is in S prime as well. So let's just remember what S and S prime are. S and S prime, right, they're the prefix of bidders in density sorted order whose total size is less than B, less than the number of seats on the plane. And what's the difference between S and S prime? Well, the only thing that has changed is that bidder I has raised their bid. So the densities for all of the bidders other than bidder I, Vj over Wj, those remain the same. And the density for bidder I has increased, raised his bid, and his size hasn't changed. And so when he raises his bid, he can only move himself earlier in this density sorted ordering. His density went up, but nobody else's density changed. And so if he was already in S, if he was already early enough in the ordering to fit on the plane, then by raising his value and moving himself only earlier in the ordering, he'll still be early enough in the ordering to fit on the plane. So by raising his bid, if he was already in S, he hasn't taken himself outside of it. And so if we are in the case where in both instances of the algorithm, these sets S and S prime were chosen as the set of winning bidders, then in that case, we're done. That's one of the cases. And if T, the winning bidders, were S when we ran the algorithm on the original bid, and S prime when we ran it with the raised bid, then we're done. How about the other cases? Well, note that if bidder I was in this set S, if before he raised his bid, bidder I was already in the prefix of bidders in density sorted order that fit on the plane. And given that when he raises his bid, he continues to be in that set, when I look at the total welfare of people in S prime, that's only going to be bigger than the total welfare of people in S, because the only change was that bidder I raised his bid, and since if he was in S, he was in S prime, that increase was entirely accumulated within the set S prime, right? So nobody in this set decreased their value, and like bidder I increased his value, and so nothing changed. And so in particular, since we choose what the algorithm chooses what set to output by comparing the welfare of the people in S with something else, if before he raised his bid, the algorithm output set S, it'll still output set S after he raises his bid. Okay, so if T was S, then T prime was S as well. And so there's only one remaining case, which is that it might have been that bidder I won the auction before he raised his bid, but not because he was in this set S, but rather because he was the single bidder who had the highest value. That could happen as well. But note that if that's how he won the auction, it was because even before he raised his bid alone had higher value than the entire cumulative bids of everyone in the set S. That was why we might have output the singleton set. And so in this case, by raising his bid, bidder I must also continue to be the winner. How come? Well, if he was already the high bidder, if he raises his bid, he's still the high bidder. And so if after he raises his bid, the algorithm continues to output the singleton set containing the high bidder, well, it's still him. He still wins. Now, it's possible that after he raises his bid, the algorithm doesn't do that anymore, right? Because it might be that the welfare of S prime increased after he raised his bid. But the only way that could have happened is if he raised his bid enough so that he moved early enough in this density sorted ordering that he was in S prime. And so in that case, he wins as well. Okay, so for this algorithm, there's no way to raise your bid that causes you to go from winning to losing. So the algorithm is not only a polynomial time 2 approximation for the knapsack problem, it is monotone non-decreasing, which means the payment rule we covered last lecture makes it a dominant strategy for people to tell the truth. Okay, so even though we have a truthful mechanism that approximates welfare in this allocation problem, whose welfare optimization objective is NP hard, the VCG mechanism wouldn't have done that for us, but our characterization of single parameter domains helped out. Okay, so I'll see you guys next time.